So guys, we're back again for another video, but this time we'll provide audio for this PowerPoint presentation on examples on slope stability. So let's start. For this first situation, we have here, for the soil properties given, we have here a specific gravity of 2.68, a void ratio of 0.65, an angle of internal friction of 26 degrees, and a cohesion of 14.4 kilopascals. On height of the soil is 3 meters. And we have here the angle of the soil as 20 degrees. So first, compute the factor of safety against sliding along plane AB. A seepage through the soil is present and the groundwater table coincides with the ground surface. We have here number 2. Compute the factor of safety along the soil-rock interface if there is no seepage. And for the last one, find the critical height of the slope. So let's just first solve this one. So in this case, we could see that there is a groundwater and the soil is fully submerged with the groundwater. So it spells out something, and that would be the gamma saturated. So we are to solve again. Gamma saturated, that would be GS plus E times gamma of water over 1 plus E. We've learned that in our past videos, so I'm really not going into it here. So let's just go for the factor of safety. So we could use the equation of the factor of safety, using C over the gamma saturated, since that is saturated, times the height times sine beta, cosine beta, plus the gamma submerged times tangent of phi over gamma saturated times tangent of r beta. Now, gamma submerged is also equivalent to having gamma saturated minus gamma water. So here we will have a factor of safety of 1.43, quite safe. Next, compute the factor of safety if there is no seepage. So if there's no seepage, there's no given moisture content, then we could just solve for the factor of safety using the other formula of C over gamma times height times sine beta cosine beta plus tangent of phi over tangent of beta. And here we will have a factor of safety of 2.28. Another easy one. And for the last one, find the critical height of the slope. For us to determine the critical height of the slope, we must know that the factor of safety should be 1. So in this time, the height is missing, the factor of safety is given. So equate factor of safety as 1 into that formula a while ago, then we will have the critical height as 6.99. But what does this mean? If the height is lesser than 6.99, then the factor of safety goes up, which means that this angle would still support the soil at that certain height. If the height goes beyond 6.99, what would happen? The soil would be similar to having a landslide. So this angle cannot really support that certain height. So in order for us to determine the critical height, the factor safety having that safety net should be equal to 1. So in this case, at the height of 6.99, this is still safe. So next we have here the second problem. A cut slope consists of soil materials that has a unit weight of 16.42 kilonewtons per cubic meter and undrained shear strength Cu of 27.8 kilopascals. The soil makes an angle of 50 degrees with the horizontal. Assuming that stability number is 0.162. Compute stability factor, compute the maximum height to which the cut would be made, determine the angle that the failure plane makes with the horizontal if BC has a value of 7.93 meters. So let's go into this problem. First is to compute the suitability factor. It's actually quite easy. It's directly in the formula. To solve for the suitability factor, you just need now your stability number. And 1 over the stability number would be your stability factor. Now number 2, compute the maximum height to which the cut could be made. Now if we could remember the equation of our stability number, we should know that M, or the stability number, is equal to cohesion over gamma times the critical height. Here we could just substitute the values. And we could get now the critical height as 10.45. For the next question, we are to determine the angle that the failure plane makes with the horizontal if we have BC as 7.93. Now we could just use trigonometry. The tangent beta could be equal to critical height over x. Then we could get the value of x. Now that we have the value of x, we could add it to 7.93 for us to have the distance from A to C horizontally. Then here we could get now the angle that the failure plane makes with the value of 32.04 degrees. Now for our last problem. A cut slope is to be made with the unit weight of soil as 17 kilonewtons per cubic meter, and the angle of internal friction is 20 degrees. The soil has a cohesion of 28 kilopascals. The cut slope makes an angle of 30 degrees with the horizontal having a height of 9 meters. If the trial failure plane is 15 degrees from horizontal, determine the frictional force along the failure plane, cohesive force along the failure plane, and the factor of safety against sliding. So first, we will have here the frictional force along the failure plane. We should first determine the distances needed. If we have here a height of 9, we could just provide here the value for the x, through which we could use tangent 30 to be equal to 9 over the x1, or the distance here from A to that hidden line. And then of course, we again use the value of our height 9 and use tangent 15 for the failure plane. So, tangent 15 would be equal to the opposite 9 over the distance horizontally between A and B. Now, we should always remember that in doing this, we should consider a meter strip in volume. So now we could get our mu as tangent phi. So tangent 20 would be equal to 0.364. That would be used for our frictional force. If you could remember your physics or your dynamics, mu is partly needed in friction. So next would be the weight. We could get the weight by having gamma, or a unit weight, multiplied by a volume. And in this case, we should have the weight above the failure plane. So we need to get the volume of the soil above the failure plane AB. So to get that, we could use the triangle minus this small triangle. Take note, we are to consider 1 meter strip in the width. Then here would be the volume. Multiplying it with our gamma, we could get now the weight above the failure plane. Using the weight, we can now get our normal force N as W cosine theta. Then we can now proceed to having our frictional force, mu N, same as the one we're using in physics. And it would be equal to 0.364 multiplied by 1,377 times cosine 15. We will have a frictional force of 484.15 kilonewtons. Number 2, cohesive force along the failure plane. We should first know the length of AB. So to get the length of AB, we can use sine theta. Sine 15 degrees is equal to the opposite over the hypotenuse AB. To get the length AB now, 9 over sine 15, we could get 34.77. Why? Why do we need this? Because for the formula of our cohesive force, we need cohesion and of course the area AB. Now, we need again to consider 1 meter width strip. So, cohesion multiplied by the length AB times 1 meter, we could get now the cohesive force as a value of 973.56 kilonewtons. Now, for the last one, to solve the factor of safety against sliding, we should have the frictional force, we should have the cohesive force, we have W weight, we have theta, then we could already solve for factor of safety. Now in here, we have factor of safety of 4.09, quite high. which means that this type of slope can withstand that certain height of soil. So this is still safe against sliding. Always remember, having a low factor of safety is not good. Having a high factor of safety means that it's quite safe. So thank you for watching. Until next time, peace.